So the Arrhenius equation looks like this, where K is the rate constant, A is the frequency factor, E is the natural base, lowercase e. E sub A is activation energy. R is the gas law constant. And since we're dealing with activation energy, we're going to use 8.31 joules per mole Kelvin, which makes T Kelvin temperature. So this relates the rate constant, which we can take back to our rate law, to collision frequency, which is concentration, orientation, activation energy, and temperature. However, this A, this frequency factor, is dependent on the reaction. So it changes with each reaction. Each reaction has its own frequency factor. So again, we need to look at a way that we can kind of avoid using the frequency factor or knowing what the frequency factor is if we're in the lab and we're trying to determine the activation energy for a reaction. So as it turns out, if we transform this equation by taking the natural log of both sides, we can get a graph that looks like this. Remember, Arrhenius equation was K equals A e to the negative EA over RT. So natural log of K, the natural log of E to the EA over RT gives me the 1 over T and a slope of EA over R. So I basically get rid of that log. And because A is multiplied by E, I'm adding A to that E. So that gives me a linear plot. So if I'm looking at this graph, I can see that I have a straight line. So if we remember, for an equation with a straight line, y equals mx plus b. So if we look at what we have graphed, we can see y is the natural log of k, m is negative EA over r, my x is 1 over t, and although this particular graph has a definite value for the y-intercept, in general, that's going to be your frequency factor, which is A. So the Arrhenius equation, rewritten in slope-intercept form, looks like this. This means that if we're in a lab, there are ways to determine K at different temperatures for a given reaction. So we can plot that experimental data and determine the activation energy.